Okay, so I'll just talk over this while it goes. Just move it along to try. Okay, you can actually see that what we've actually done here is to layer the air pollution surface, which is nitrogen dioxide. This is one of the pollutants. And the way this is done is a hydrodynamic model of London which links the pollutants which are observed in the pollution monitoring network to the model. It then synthesizes this with a traffic model because the pollutant observations are a very coarse grid across the city. There are many pollutants which are monitored continuously and made available over the web, in an archive, etc. So you can pick this data up very easily. But then to actually get the resolution here, they build a traffic model. Traffic, the behaviour of traffic relative to pollution is quite well defined. So what essentially they do is to tag, they calibrate the model in this sense to the pollution measures. They actually produce all the street canyon effects, etc., using the traffic model, and that produces a layer of different pollutants. So you can see that the intense pollutants are this red all the way through to the blue, which is in the background. And one of the features is that this particular pollutant, nitrogen dioxide, is actually associated with traffic starting and stopping in big intersections. It's associated with tunnels. It increases massively as the traffic goes through tunnels, etc. So we can do this for many different sorts of pollutants, and it brings it alive by layering it. So we're synthesizing really a traffic flow or a pollution flow model with the actual geometric model in this particular context. So this is an example of the kind of thing I think that we're going to see increasingly in the next few years, this synthesis of the geographic, the process-based modelling in this particular context with the representational model. It's the merging of the symbolic with the iconic in this particular context. Okay, let me get out of that and see if I can get back to my my PowerPoint. Okay, there we go. Okay. Of course, once we've actually got our model in this particular context, one of the most interesting features too, which is quite surprising, again, it's not so surprising now, but it was surprising 10 or 15 years ago when people first began to do this, is that we can actually print the model in a sense. So we've moved from the real model, or the real world in this particular context, through various abstractions, etc., representational, and then symbolic as well, into a form where we can build a model as you've seen it, we can fly through it and so on, we can manipulate it, and then we can actually print it, just as we can print a map from a GIS in that sense. Clearly we can actually print the model in that sense. And this kind of fabrication, again, is particularly useful. It's not been widely exploited as yet, although I think we're likely to see an explosion of this kind of fabrication, clearly not just for digital models of this kind, but any kind of digital representation. We're going to see an explosion of this in the next few years as these 3D printers become extremely low cost and popular. In fact, we have a simple 3D printer in Casa that actually spends most of its time printing the parts to build another 3D printer. There's a project, slightly sort of eccentric project in the British University system from the Joint Information Systems Committee, where somebody at Bath invented this 3D printer, which is used to actually print itself as well as to fabricate things, and they've given this low-cost 3D printer to the parts to a number of groups around the country, with the view that they will then print the next printer, as it were, that's given on to the next. It's a bit like a Ponzi scheme, like a chain letter in this particular context. But nevertheless, we're beginning to see this kind of surprising development in a sense. And you could then say, can we complete the loop, as it were? Here's the models, the fabricated realities, sensing the realities, matching the observed realities, and these are lots of different representations of 3D models, 3D representations. So we're in the world of the iconic still in this context, not one model, but many. Okay, let me just check for time. I'm conscious of this. I've got a deadline of about probably 10 to 11 in this context. So I'm going to move on now to talk really, well, one last thing I'd like to show before I do move on, but I'm going to be moving on to different sorts of models into more the traditional fields of urban models, which are essentially sort of cellular automata and active transport models. Okay, one last thing, of course, is that, and I said this way back, that once we actually have the media, in some sense, the 3D model itself, and indeed any media, we can import this into a whole variety of virtual worlds. Now, this is a virtual world called Unity in this context, and this is it should. My problem here with the never do this on an old 4-year-old laptop. That's the essence of. Let me try and get this to the right size. Okay, so all you're going to see here is somebody dancing around, basically, sort of. But the key issue here is that we can import much of the media of iconic, analog and symbolic modelling, and you can see here agents over a surface. This might be some kind of biological problem, or it might be a traffic problem in this particular context, but all we're doing in this context is to import the symbolic model into an iconic representation. There's a map of GLA, it's output area classification, geodemographics in that sense, so this is really a virtual exhibition space in this particular context. And you can actually see a variety of things being put into this particular context. And of course, we can enter the world itself as avatars, and we can engage either directly or normally remotely, as it were, because these things are web-based in some sense, and engage in some kind of dialogue. So to some extent, again, this is an example of the convergence that's taking place in this field as lots of things come together. And I think that's going to be the characteristic of the next 10 or 20 years, how we're beginning to put things together and produce very surprising and interesting and innovative and mind-boggling things that we really need to think about, many of which may be not really useful at all, but some of which will be useful in ways that we've not really anticipated. So to some extent, this is the future. Okay, let me go back to the PowerPoint and here. And say something very quickly about principles of modelling. One of the key issues is simplicity. That I've talked about abstraction. Models are abstraction. We lose information. So simplicity is one of the basic canons that we actually work to in scientific modelling. Now, the idea of a model being relatively simple, there is something called Occam's razor, which is a kind of a folklore in philosophy that says that if you have a complex model that produces an answer, and you have a simple model that produces the same answer, then choose the simpler model in that sense. In other words, get rid of any superfluous detail in this. So this is the principle of parsimony. Now, in fact, this principle of parsimony, in my view, is up for grabs in the modern world, in a sense. That the idea that we should be as simple as possible, etc., in some senses, even if we know there are things out there that are relevant in a sense, is beginning to change. The idea that simple models are better than complex models, even though we may not be able to test in a traditional sense a complex model, is a principle that is under great scrutiny at the present time. The second principle is repeatability. It's a good canon of science that if we develop a model for Delft, for example, then the really true test of the model, and this is what Larry says in his paper, is to see whether it works for Dordrecht, etc. In fact, when I gave this talk, or a version of it last week, it was in Delft, and I probably should have said Braga and Lisbon or something like that, but, or Coimbra and Lisbon. But nevertheless, you get the point. That in other words, we build a model for Lisbon, and really to see whether it works or not, strictly speaking, we should see whether the model then works for Madrid. Now, to some extent, as soon as we pose the issue in these terms, we know in our world that that's not going to be the case. That in some senses, the idea of repeatability, a generalizability in a science, in a lab context, in an experimental lab context, is not really a principle that we can hold dear in our particular field. We know that the world is too complex, and this is one of the main reasons, I think, that the idea of making analogies with classical science in terms of our world, even classical science itself is under scrutiny in terms of these sorts of issues at the present time. It fit the world 200 years ago when life was less complex in a sense, but perhaps no longer. Now, the third principle is falsifiability. This is Karl Popper's canon that says that you can't prove anything right, or you can prove it wrong, and good theory, good models, good science withstands the test of time only insofar as it cannot be shown to be wrong. But because we can't predict the future, certainly in the social world in that sense, then in some sense, and because we have control over the future, we have our own ability to mold the future in that sense, then to some extent we could never prove anything right in that sense. So this is again a basic issue that really begins to weaken the idea of predictive modelling. Many of these principles or canons, if you like, of science, which are under attack or under scrutiny, are really to do with the notion that prediction is not what it originally seemed. To some extent, this is weakening our ability to use these in a classical predictive context. Okay, let me move on. Okay, the last part of the talk is really going to be on some of the challenges that face us in terms of building models of systems, in a sense. I'm going to pick out three and then illustrate them in a little bit more detail. Now, I mentioned these right at the beginning. I want to talk about questions of detail, the development of new styles of model where we're actually building more and more detail in, conflicts immediately against this principle of parsimony or simplicity in some sense, but nevertheless, we are now in a position where we can actually do it. 30 or 40 years ago, with computers being used to develop aggregate models, we couldn't really do it in that sense. Agent-based modelling and cellular automata modelling, some of the examples I showed you of these agents working in these spaces, etc., are models that could never be tested in any traditional scientific sense, but nevertheless have been built largely because we feel that these are important in terms of thinking about particular questions in hand. Now, the second point is the question of visualization. To cut through the complexity, visualization is all important. We've seen examples of that this morning. We're going to see them throughout the conference. And then finally, the question of model integration. No one model ever fits a single problem context. Therefore, of course, this often leads us to design specific models for specific contexts. Because every context has its own idiosyncrasy, we're often forced to think of adapting a particular style of modelling to a context, but another strategy is to add together different elements of models and to produce some kind of integration in this way. Now, I'm going to show three examples very quickly. The first is some work done by Kirill Stanilov in our centre, where he's building a relatively simple model of the historical development of West London, using a package called Metronamica from the Knowledge Institute at the University of Maastricht, the RICS group there. This is a standard package for cellular automata, and this changes the notion of what is being developed and what can be predicted. The second example is our